Welcome to the final part of this lecture. In the previous two parts of this lecture, we firstly introduced life cycle analysis as a tool for chemical engineers, and then we had a look and established the baseline metrics for polyethylene terephthalate production. What we're now going to do is see if we can answer some questions about biomass substitution and about recycling and quantify their impacts relative to the baseline we've established on the environment. What we'll see in some cases is that biomass substitution can make some metrics better whilst making other metrics worse. We'll also see that the type of biomass we substitute and where geographically we do it can have a very, very large impact on those results. We'll also see that recycling makes the results for certain metrics a lot better almost regardless of how we do it, which is some very good news indeed. So let's start off by reminding ourselves about the production process. So I'm displaying to you now the production process for polyethylene terephthalate we examined last time. The blue boxes are the process models that had to be made for this study. The red boxes are pre-existing literature, and both of these blue and red boxes underpin the fact that a lot of data is required in order to carry out a life cycle analysis. So what we're going to do is to deconstruct the value chain. We're going to say, let's try and substitute some biomass. And so we're going to remove a little bit of crude oil now. See, that red box has gone. Now, what we're going to do instead is to put another production process in that makes ethylene. So we're going to get bioethanol from sugarcane and make ethylene from that, and make the required amount of ethylene from that biological feedstock required to make our functional unit ultimately. Now, the bioethanol process alone isn't sufficient because of course that biomass has to come from somewhere. And so in the first case we're going to examine what happens if we use Brazilian sugarcane, which is very rich in sugar for fermentation, to make that ethanol. So here I'm now displaying the modified production process. We've removed the crude oil, we've added in a biological feedstock. So, does this make things better? Does this make things worse? Or is the picture actually a little more complicated than that? Let's find out. Let's look at our energy use to start with. Here with the Sankey diagram for the petrochemically produced polyethylene terephthalate. One of the big take-home messages here is that the focus on energy reduction should really be on the acid production step. That pure terephthalic acid is a major energy use in the overall process. So what happens if we use bioethanol instead? Well, let's deconstruct part of the ethylene route. So we've removed the crude oil required for ethylene production, we've removed the energy required for crude oil ethylene, and we're going to now add in our bioethanol. So there is a production box for bioethanol to ethylene, and then we need to make that bioethanol. And so what we need there is a lot of biomass. So there on the display now is that biomass route. If you look at the bioethanol production box, we can see there's an imbalance there, and so the balance must be processing energy. And so what we see is we actually increase our processing energy for a functional unit from 1.6 megajoules right up to 1.97 megajoules. And so by introducing biomass as opposed to crude oil derived ethylene, we've actually increased our energy overheads, which might come as quite a surprising result. So at first sight, maybe this doesn't seem to be the improvement that it could be. Let's look in a little more detail. So I'm going to look at some key sustainability metrics alongside global warming potential for the Brazilian bioethanol produced polyethylene terephthalate. So I'm going to be presenting these results as a change from the established process that we looked in the last part of this lecture. That's why we looked at the established process in so much detail. What we want to do is to rank different processes against that process and then see whether they're better or worse, or better in some areas and worse in some areas. So I've chosen 5 different environmental impacts: global warming potential, abiotic depletion, resource use, acidification potential, acid rain basically, ecotoxicity potential and eutrophication potential. And I'm going to be plotting each of these as a change from the datum that we established last time. So, let's start off with global warming potential. If we use Brazilian sugarcane bioethanol to make ethylene, actually we do reduce the overall global warming potential of the process by some 25–26%. So that's good. In terms of abartic depletion, we reduce that a little bit as well. However, if we look at acidification, ecotoxicity and eutrophication, we see very large increases with reference to the datum. And this is the complex picture that life cycle analysis presents. Very usually there is no straightforward, simple answer saying this is better. It's far more nuanced. The answer is usually with some impacts you see an improvement. However, with other impacts you may not see an improvement and you may see the situation getting worse. What's important? And that is the judgment question. If the only thing you care about is global warming potential, then this is an improvement. However, if you care about the environment more holistically, then look at the eutrophication potential. The amount of fertiliser required to grow the sugarcane causes very great loss of life in rivers and waterways. Can you put up with that to offset that global warming potential? Is it worth it? A very, very pertinent question that goes sometimes beyond the role of chemical engineering. So, it's not all good. Some things are good, some things are not. Now, what happens if we use a different source of bioethanol? What happens if we use a cellulosic feedstock sourced locally within the UK for UK production of plastic bottles? So we've changed our definition slightly because we're now looking within the UK for the manufacturing process. What happens if we use willow trees? Well, let's look at the same metrics. Global warming potential is reduced, but not quite so much. There's not quite so much sugar required in willow, and so there's a lot more processing steps required to willow to ferment up the bioethanol in the first place. So we find that abartic depletion is reduced, again, by not as much. However, acidification potential is reduced. It's still greater than the petrochemical process, but it's less than the Brazilian bioethanol process. Ecotoxicity, however, is lower than both the datum and the Brazilian bioethanol case, and eutrophication potential is similarly lower. And so we have a very graphic illustration here that where you source your biomass from and what type of biomass you source has a very, very large impact on the sustainability metrics for process improvement. We haven't changed the process when we look at these data. The process that is pertinent to these data is the same. We're still using bioethanol. We're still using bioethanol to make ethylene. And then we're still using the existing petrochemical value chain to make polyethylene terephthalate. However, the source of biomass is really very, very important vis-à-vis the environmental metrics. So what's the conclusion? The conclusion is that there are very difficult choices to be made. Do you prioritise global warming potential against all other forms of environmental impact? And if so, maybe Brazilian bioethanol is the way to go. But that's only part of a very large and complex picture. If, however, you decide that a holistic picture is important, maybe domestically produced bioethanol from cellulosic feedstock is actually the way to go. You don't reduce global warming potential quite so much in the ethylene production, but overall we know that the focus needs to be on pure terephthalic acid production because that's the major energy user. And so maybe a smaller improvement in the environmental metrics for the ethylene step can be offset against far larger gains against a different processing step within the same value chain. It's a complex picture. Now, what about recycling? Let's assume for the time being that global warming potential is our key environmental metric, and what our aim is to try and incentivise people to go out into the environment and clean it up, to try and reduce and remove the plastic pollution that has accumulated. Does this have an unintended consequence in terms of making an environmental impact, global warming potential, worse? So I'm going to put up 3 sets of data for you. These 3 sets of data refer to typical mechanical recycling operations taking place in different countries. If we look at the US to start with, we can see that the virgin polyethylene terephthalate, the first bar right next to the y-axis, has a global warming potential of around 85 to 86 kilos of CO2 equivalent per 1,000 bottles. However, if you use recycled polyethylene terephthalate, that drops to about 65 kilos of CO2 equivalent. And so we can see that there is a reduction in global warming potential if you use recycled polymer. Okay, we've seen that location can greatly influence metrics. What happens if we look elsewhere in the world? Let's look at the UK. We see a similar trend. We see that virgin polyethylene terephthalate production has more of a global warming potential than use of recycled materials. But interestingly, we see in absolute terms that both processes are lower than their US counterpart. This is largely down to the type of energy that you get from power grids. The UK power grid typically is a lot greener than parts of the US power grid. We've got more renewables on our power grid these days. And so when we think about the electricity use, it doesn't have as much of global warming impact. What happens if we look elsewhere in the world? What happens if we look at China? Well, we see the same general argument in terms of recycling has a far lower or immeasurably lower global warming potential than use of virgin polymer, but we also see that the absolute level of emission is higher than both the UK and the US. Again, this is down to the power mix within the country's grid system. China relies a lot more on coal power than either the UK or the US, and so per unit of energy used, there is far greater CO2 equivalent emitted. And so the take-home message we can get for this is use recycled polymer where possible. The politics of this is how do you implement this? How do you incentivize people, A, not to throw stuff out, and B, is it financially viable to incentivize people to go out and harvest waste polymers? Food for thought. Politics and engineering, unfortunately, do run hand in hand. Let's discuss a few key points. What I wanted to show you was that in some ways, biomass substitution can improve some sustainability metrics for the production of the functional unit that we've chosen, our polyethylene terephthalate drinks bottle. But you have to be careful what environmental metrics you look at and what biomass you use. The choice of the wrong biomass can actually make a lot of environmental metrics worse. Does this matter? Should it matter? Which environmental metrics are more important? Are all environmental metrics equal? These are more complex answers that go sometimes beyond the realm of engineering. Because if we use the wrong substitution route, we can significantly worsen some environmental metrics over others. We've seen that in this case, a recycling operation improves environmental metrics. And maybe again, beyond engineering, but there should be incentive for people to recycle more and to gather waste from the environment and put it back into the value chain. The theme that runs through here is there are always going to be compromises to be made. Significant improvements in one area may result in significant degradation to another. How do you make that choice? Quantitative methods such as life cycle analysis can be used to inform choices and hopefully make those choices somewhat less arduous and difficult to make. Quantitative methods such as life cycle analysis are also very good areas for chemical engineers to work in because very good understanding and very good modelling of the processes that are required to make things is needed. And so hopefully with life cycle analysis and good decision making, chemical engineers can help make informed choices about future technologies that are environmentally benign compared to their past counterparts.